Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Allison Glantzberg and Nancy Chabot with us today. Hello, Allie, and hello, Nancy.
Hi, thanks for having us.
Oh, well,
yeah, great to be here. Thanks.
Yeah, well, thanks for agreeing to talk about your very lovely article. It's a very nice one. And Allison, where are you located at?
So I am home right now, but I am located in the Laurel, Maryland area, which if you don't know is like equidistant to Baltimore and DC, maybe a little further from DC.
Right.
And so it's here that I work at the Johns Hopkins University Applied Physics Lab.
Oh, very nice. APL, very nice. And Nancy?
Yeah, I've been at the Johns Hopkins Applied Physics Lab for 18 years now. And so, yeah, it's been a great place to work. And we have a long history of Mercury here, having built the Messenger spacecraft. So super excited that we were able to do this study and carry on with that.
And that's a very lovely background there you have, Allison. Love that one. And Nancy, you've got some pictures of South Pole stuff over your shoulder. Were you doing Mercury stuff there or other stuff there?
Oh, it's a little too cold at the South Pole for Mercury. So, but there is ice. So I suppose there's that. No, I've been with the Antarctic Search for Meteorites program 5 times. And so those are sorts of fond memories of field teams down there collecting meteorites in the Antarctica.
Very cool. Very cool. And Allison, you were a graduate student?
I technically am a part-time grad student at JHU working on my applied physics degree, my master's degree, but I work full-time at APL.
Very cool. And what do you like to do for research, Allie?
I mean, I have a lot of interests, but most recently I got to do this work with Nancy on planetary science and on Mercury, and I can safely say that I really enjoyed it.
Very nice. And Nancy, what do you like to do for research?
Oh, all sorts of things. I think I'm definitely a solar system person and maybe more rocky sort of solar systems even at this point, but I got my PhD in experimental geochemistry, so big in the meteorite community. I'm president of the Miracle Society right now, so meteorites are always close to my heart.
Awesome.
But then applying that further out, so with the Messenger mission, and then I was really involved in the DART mission, where we just crashed into the asteroid Dimorphos. So kind of this combination at APL of working on missions and research works well.
Awesome. Very cool. And that is going to bring us to this very awesome PSJ article. And there we go. Planetary Science Journal. It's open access, people. We are in the open access era, so you can go get a copy for free. Go grab one. Investigating the stability and distribution of surface ice in Mercury's northernmost craters. And Allison, Nancy, take us away.
Thank you. So first, let me acknowledge all of our incredible co-authors: Michael Barker, Erwan Mazarico, Matthew Siegler, Jose Martinez Camacho, Colin Hamill, Edgar Rivera Valentin, Heather Meyer, Stefano Bertone, and Ariel Deutsch. So we're very grateful for all of their help with generating the models and all of their inputs with the paper and all of that good stuff. So big thanks to them. Do we want to just go to the intro?
Sure, let's start walking through the intro.
So in the early 90s, some Earth-based radar telescopes found deposits that were bright in the radar wavelengths. These observations shared characteristics with radar observations of other known icy bodies in the solar system. So the 2 examples that are always cited, and they're cited in my paper as well, is the South Polar Cap of Mars and the Galilean satellites. So because of this resemblance, it was thought that these deposits could be water ice. But radar can only convey so much. We don't know the depth that this material is at, and there are other materials that can be bright in radar. So we needed to send a spacecraft to orbit Mercury to investigate these deposits a little bit more. So Messenger, the Mercury Surface Space Environment Geochemistry and Ranging spacecraft, was the spacecraft to orbit Mercury for about 4 years. And Messenger was an APL-led mission. APL is where Nancy and I work. And I believe Nancy was the instrument scientist on the Mercury Dual Imaging System. Is that right, Nancy?
Yeah, that's right. It was really great to be in charge of that camera and the team while we were seeing the planet Mercury for the first time. I mean, before Messenger, we had only seen 45% of the planet, if you can believe that, right? Like a planet right here in our solar system. So we got to make the first global maps, and it just is such a great data set.
Very cool. Very good.
Yeah. So as Nancy was saying, like there are a few instruments, well, Messenger had a lot of instruments, but a few that were valuable for this study. in characterizing those radar bite deposits. So the Mercurial Imaging System images mapped the entire planet for the first time. The Mercury Laser Altimeter collected information about the elevation and also the reflectance, the albedo of the Mercury's surface, and the neutron spectrometer, which gave us some, we're not looking at that data set in this study, but it did tell us some valuable things about those deposits.
Absolutely. Cool.
So both the MDIS and MLA enable the derivation of maps of all of Mercury, so the shadowed regions, and that enables us to generate models of the North Pole, so the thermal conditions and the volatile stability depth. And MLA also gave us an abundance of high reflectance values that found those values in the northern region where those radar bite deposits reside.
Okay.
This material was about a factor of 2 brighter than the average reflectance of Mercury. So it has been interpreted as evidence for actually exposed water ice at the surface.
Okay.
Now, the neutron spectrometer found elevated levels of hydrogen in the North Pole, consistent with those radar bite deposits being composed primarily of water ice. So all of these observations were made that indicate that there is not only water ice on Mercury, but actually exposed at the surface in some parts. So in fact, some of the models that were generated show these extensive regions within these large northern craters that are able to sustain water ice at the surface.
Okay.
So a few of those craters, the ones that we're focused on for this study, Kandinsky, Tolkien, Chirgavadotter, and Chesterton, they have been studied before, but it was determined that they likely did have water ice at the surface, but the extent and the precise boundaries on the water ice could not be determined due to the limited messenger data.
Okay.
So in this study, we want to look at these craters in a higher level of detail than what has been done before.
Cool.
See if we can actually see any ice at the surface and identify the boundaries and the extent of that ice, and see if our findings actually agree with models. So Nancy, is there anything that you wanted to add to that?
Yeah, I mean, I think just a little bit too. I mean, you did a good job introducing it. I kind of remember, right, when we were living this and the new images were coming up and we're seeing the planet for the first time. A lot of the studies that we did on Messenger were so global, right? Because you just had never seen it before, right? So you're talking about the whole North Polar region. So it's been really fun on this study then to look at these 4 specific craters, you know, and dig into it at a different level. And so for me, it's been exciting because we were just so busy commanding the instrument, getting the data, doing these models for the whole pole. And now to be able to dig into it with this study has been great.
Very nice. Very nice. All right. Methods. What
On to the methods.
What did we do?
So if you want to, I guess, scroll to figure 1.
Sure. Let's take a look at figure 1. Maybe
I love figure 1. It's so pretty. He did such a good job with this.
Beautiful. It's beautiful.
So these are actually what the models look like. Previous studies, as Nancy was saying, were global. They were like of the entire northern region. We had models at resolutions of 1 kilometer per pixel, 500 meters per pixel. A very recent study published models of these craters specifically at 250 meters per pixel.
Okay.
But we needed higher resolutions than that. So these models that you see here are at 125 meters per pixel.
Very nice.
And so 1A is the digital elevation models from left to right, Chesterton, Chirgavadotter, Tolkien, and Kandinsky. They were produced with the Mercury Laser Altimeter data, which gives us directly information about the elevation, but we supplemented these models by applying shape from shading techniques to the Mercury Dual Imaging System images. So I think this helped resolve the outer edges of the craters and the sunlit regions. So with these new digital elevation models, we can model the sunlight that's incident on the surface of the craters, which is what you see in 1B. This shows the maximum solar flux over the course of a Mercury solar day, where the white region represents the permanently shadowed regions, or the PSRs. These, as you can see, span about the entire crater floor. Now, knowing how much sunlight is incident on the craters, we can model the temperatures of the surface. So we have the maximum temperatures in 1C and the average temperatures in 1D. Important thing to note is that the scale, the color bar scale, is different in 1C and D.
Yes.
So the average temperatures are actually much cooler than the maximum temperatures than they might appear. But even so, at maximum, most of the crater floor, most of the PSR is still very cold at temperatures of 100 Kelvin or even less than that. So knowing these temperatures, we can model the volatile stability depth by considering the thermal parameters of those volatiles,
the
specific heat and the thermal conductivity, and I think the density. So that's what 1E and 1F are showing. So in 1E, we have the volatile stability depth of coronine, and in 1F, we have water ice. Now, coronine might seem a little bit random,
Yes,
but it is
it's there.
important because we're talking about water ice, and then there's just what is coronine.
What is coronine is.
Yeah, so it's important because previous studies have found this low reflectance volatiles at the surface of some lower latitude craters.
Okay.
And this low reflectance material has been suggested to be a mixture of complex macromolecular organic molecules. And in one study in Hamel et al. 2020, coronine was found to have stability boundaries that agreed really well with data and observations. And Nancy was on that paper, worked with Colin. Is there anything you want to add about coronine?
I mean, yeah, it's definitely just representative, like you said. I'm so glad you pointed it out and called it random, right? Because everybody's always like, why coronine, right? And it is just representative. In actuality, we think it's a whole medley and myriad of these complex organic compounds that are there. But it does seem to have strong evidence for these compounds are stable to higher temperatures than the water ice, and it does seem to be consistent with these higher temperature locations.
Very good.
Yeah, you can see the stability of coronine is stable to much shallower depths than water ice, which why all that blue is.
Yes.
So it's thought that like the water ice might be mixed with these low reflectance compounds, and then the water ice would sublimate as it would in these low latitude craters that are too warm to sustain ice long term. And then it would leave behind this low reflectance material at the surface that would work to actually insulate the water ice beneath it. And so we think that the processes that govern the composition of those lower latitude craters might also reasonably govern the composition of the high latitude craters that we're looking at for this study.
Fair enough.
So in the regions that are too warm to host ice at the surface on geologic timescales in our 4 craters, so in figure 1F, where it's kind of like dark blue, we might expect to find some low reflectance material there. So that's why we're modeling coronine. It's low reflectance. It serves to contrast the high reflectance ice. It can maybe help us identify the extent of the ice and the boundaries, all of that good stuff. So the white regions in these 2 subfigures, E and F, represent where the volatiles are actually stable at the surface. So even though water ice has much lower stability boundaries and is stable at much greater depths, in the PSR, it can still be stable at the surface.
Yeah. Okay. Cool.
So yeah, so I think, just coronine is just a proxy. It might not even be there. It might be a bunch of things. But we're just using it for modeling purposes.
Okay.
So I guess figure 2.
Okay. So I'm with you. Awesome. Very good. Those are beautiful figures. Figure 2. And we're going to zoom in on some of the water ice and low reflectance stuff. Okay.
So this is basically those white regions that you saw in 1E and F, the coronine and ice stability depths, just overlaid again. So this is showing our prediction, right? The regions that are red represent where we might expect to find superficial water ice, and the regions that are blue are where we might expect to find superficial low reflectance compounds like coronine. And so we want to see if the data agrees with this prediction. So if, for example, we were to find water ice in maybe the blue parts, that might be able to help us constrain the age of the ice because it wouldn't have had time to sublimate, right? We don't expect to find ice there. So the ice was young. So whether or not the data agrees with what we predict to see still tells us something very valuable.
Okay.
So if we go to the next section, we can actually look at
that. Yes, one question here. So this is from a model. So this is a chemistry model, or what is the model here?
This is a thermal model. So we have the temperatures, and given the volatile parameters, their thermal parameters, we can model at what depth they would be stable at those temperatures. So this is where we expect them to be stable actually at the surface. I'm
with you. Okay, very good. All right, so there's our prediction. We got the data. Figure 3. K-means.
Okay, yeah. So we're comparing that prediction in figure 2 to 3 data sets: the radar data, the MDIS data, and the MLA data. Okay. So this figure 3 is showing the Arecibo radar data. To investigate variations in the radar backscatter, we applied a K-means clustering algorithm to the total power maps, which is what you're looking at. This is the Arecibo total power maps. Okay. This algorithm basically groups data into clusters by minimizing within cluster variances. So here the total power. Sorry, did you have a question?
No, I'm good.
Okay. Here the total power was clustered into 6 groups or classes, as we're calling them, where the radar backscatter intensity increases from 1 to 6, where 0 is indistinguishable from noise.
Right.
So
Okay.
in this figure, we can see that most of the high radar backscatter, like the pink and the purple, so classes greater than 4, is contained within the PSR, which is outlined by that yellow line. That's kind of a little bit hard to see. And most of the low radar backscatter is outside of the PSR, with the exception of some of the central peaks in Tolkien and Kandinsky.
Is the yellow contour more or less aligned with the crater rim?
Yeah, that's a great question. So sometimes there can be alignment problems because of the different data sets, but it's not unreasonable that we might find some high radar backscatter just outside the PSR, because we've seen this in Prokofiev.
Okay.
So they are.
Yeah, so it's not the crater rim, it's the PSR, the permanently shadowed region. So this is not a topographic outline for the yellow. It's the as modeled the incident illumination of the sun sort of in that first diagram. So that's a sort of interior to the crater rim for sure, because the crater rim gets sunlight.
Right.
Okay, good. Thank you.
Thank you. So this figure really isn't surprising. It really agrees with expectations. There's high radar backscatter within the PSR where we expect to find ice, and low radar backscatter outside the PSR where we don't expect to find ice.
Okay.
So if you scroll to figures 4 and 5, they're essentially the same. You can pick one.
Let's go for it.
We compared the maps in figure 3 to maps of the temperature and the ice stability depth by finding the average and standard deviations for each. But temperature is highly correlated to the ice stability, so that's why they're very similar plots. We noticed that from these plots, there are regions with low classes are associated with temperatures that preclude the long-term stability of water ice and are consequently associated with ice depths that are greater than 0.
Yes.
While high classes are associated with low temperatures, high radar backscatter, that permit the long-term stability of water ice. So these plots are mostly intuitive and they agree with expectations, but there's a class 3 here, which this intermediary class that has much higher backscatter than class 2, but much lower than class 4.
Fair enough. Transition.
You return to figure 3.
Yes, yes.
You can see that class 3 is primarily within the confines of the PSR, the permanently shadowed region, which is the cyan color.
Yeah.
So we believe that due to its proximity to the high backscatter regions, the pink and the purple, that class 3 could represent either ice that is buried beneath a thick mantling, ice that is less abundant than the high radar backscatter areas, or ice with a greater amount of contaminants or impurities. So all of these scenarios would reduce the backscatter that we were seeing.
Yeah, I'll give you this trend.
Basically, the radar is telling us that the water ice might not be evenly distributed, independent of the thermal environment.
Fair.
And studies of Prokofiev have found superficial ice, but they also concluded that the ice likely wasn't pure. So this really isn't outside the realm of possibility for these 4 figures.
Well, it's good you're picking up the transition, right? It's basically a region.
Yeah,
it's a little surprising that it's right in the middle of the PSR, though. That's the thing, is it's like if you look at the figure, they're like falling right in this permanently beautiful cold region where like everything should be nice and happy. So it's not like it's just all around like at the edge or anything. And so it really does seem to be telling you something about the nature of the ice there, that it's not just this nice homogeneous deposit in these craters.
Cool. Good. I'm with you. Okay.
So onto the MDIS, I guess, figure 6.
Figure 6. That's more of the backscatter. MDIS. Ooh, more. Nice. Okay, I'm going to zoom out to get a global here.
Yeah, it's a big figure.
And we can zoom in as need be.
Okay, so the MDIS, Mercury Dual Imaging System, wide-angle camera was successful, kind of, in imaging the permanently shadowed regions of these craters. How, you might ask? There's no light. How is it picking up the detail? Well, it did this by sort of compromising. So the readout edge of the CCD cameras, the charged coupled device, has to be situated along the permanently shadowed region for this to be possible. So I've labeled.
Zoom in on just the top row, actually, it would be.
Yeah.
Yeah. Okay.
Because because they're all like the 4 different craters, so we can just talk about Kandinsky first, probably. Yeah, that's cool.
Yeah, that's good. So I've labeled the CCD readout edge.
Okay.
In this first column, which are the actual images of Mercury's craters. The reason it has to be situated like this is to prevent, so in order to capture those details, we had to use a long camera exposure because the PSRs have light, but it's very minimal and it's only scattered light. And this causes the sunlit region to saturate. And the problem with this is that CCD cameras are prone to blooming, which is when the pixels of a CCD camera become saturated and the charges of those pixels spill into adjacent pixels, basically ruining the image. So in the second row in 2A, you can see that I pointed out some examples of blooming, those signature streaks.
Okay.
So if you get streaks like this across your image, that part is unusable. It's compromised data. So by situating the readout edge along the unsaturated PSR, we can prevent blooming from like ruining the image.
Okay, got
hard
it.
to spill in a certain
I'm
direction.
I'm with
Right.
you. Yeah.
So in 1A, for example, if there aren't any saturated pixels to the right, that would cause the streaks across the PSR. Unfortunately, using this technique means that we don't have any complete images of the PSR. They're all partial, like the ones that you see in this column.
Yeah.
And so we don't also, this was really difficult to do. Nancy could tell you how difficult this was, but we don't have many. So if you look at the appendix, you don't have to do it now, but there's not many images that we have to work with. Nancy, do you have any comments on how difficult it was to image these PSRs?
Yeah, we actually didn't do this until like the third year of orbital operations. It wasn't in the baseline mission and anything because it was a little experimental. And we took a lot of images that look way worse than this one. So, you know, these are beautiful as far as I'm concerned. I mean, just the fact that you can see details within permanently shadowed regions on Mercury's North Pole, where these places where you think ice is stable at the surface, you're basically seeing an image of where we predict ice is on Mercury right now, which is, you know, yeah, I'll take it.
Very
but
good.
They were hard.
Yeah. Well done. Congratulations.
So yeah, you can see the beautiful details of Kandinsky, but this is like the best one that we have.
Yeah.
So what we're looking for in these images are regions that appear bright that could be attributed to water ice at the surface, or regions that are especially dark that could be attributed to low reflectance materials.
Okay.
But we need simulated images to inform how light scatters within the crater as a function of topography and illumination geometry from the sun.
Right.
This way, we don't mistake some bright regions for water ice when it's actually just a bunch of incident sunlight in that area. So in like the top kind of corner of Kandinsky's edge, you can see that bright area. That's just sunlight. There's not ice there.
Right.
Okay. So that's what the second column is. That's all of the simulated images. They assume a uniform surface albedo. So now if we see any bright areas or dark areas in the MDIS image that deviate from what is predicted by the simulated image, we know that those areas can only be explained by some other factor, like the variations in surface composition or MDIS artifacts, which I will talk about.
Perfect.
Okay. So we try to compare these qualitatively just by looking at the MDIS and the simulated image visually. But except for Trigger, which I will talk about, which is the second row, nothing really stood out. I thought it might help if we took the ratio of the MDIS to the simulated image to see exactly how much brighter or darker the MDIS image was from what was predicted by the simulated image, which is what that third column represents. And in this ratio, we might expect that the region contained within the purple, which is the region where we expect ice to be stable at the surface, according to our prediction, to be noticeably brighter than the region outside of that purple outline.
Fair enough.
And we don't really see this with any of the images. There's no precise agreement to the predicted icy boundaries. We do, however, notice some reddening, like this gradient along the crater walls. But this reddening is consistent with being an artifact of the MDIS system due to light scattering within the imaging system during these low light conditions. But going back to Trigger in the second row, it has this peculiar feature where it's distinctly brighter about halfway up the crater. And it's the fact that this feature is not predicted by the simulated image, and the fact that it doesn't appear to conform to any sort of topography is what makes it really interesting. So this is what we're looking for. Like, here's this feature that isn't in the simulated image. Unfortunately, we think that it's an MDIS artifact. It is more pronounced in the reddening observed in these ratios of the other craters. But Trigger is also the most northern of the bunch and has extremely low levels of light. So we think it's an artifact. We don't necessarily think that it's real, but we can't really say conclusively because we have very, very little data to support or refute whatever this feature may be. We have one other image of Trigger in the appendix that shows this feature clear as day, but only the one, and the orientation of the camera is the same. So we think that this reddening is tied to the orientation of the camera, of the readout edge. And so if we had some alternate orientation, we could feel, if you want to scroll, we can feel a little more confident about
There
this
we-
feature.
This one?
Yeah, that one.
Yeah, right.
So you see the feature, but the orientation is the same. So we don't, again, it's still
Got it.
supposed that it's an MNIST artifact. And you can see that a lot of our other images kind of look this streaky, like that second row of Trigonometer, very compromised. So
Oh, yeah.
not a whole lot to confirm what this feature might be.
Okay. Okay.
So is there anything, Nancy, that you want to add before we look at MLA?
No, I think you've got everything you can out of these images that we possibly could. I mean, I think it's, it's great to see what the surface looks like, but it's been really hard to get the reflectance of the surface like definitively, for any of them from the MDIS images alone.
Very cool. Very cool. Okay. Onwards, MLA.
Figure 7. Okay. This figure,
Nice.
yeah, it's going to zoom in. Is all of the MLA data that is between 82.5 and 90 degrees north latitude, with most of the anomalous points removed.
Okay.
We couldn't remove all of them. If we removed all of the ones that were anomalous due to high emission angles, we would have no data, like none, left in our craters to look at. So just keep that in mind. It will come up. What is evident from this figure is this apparent lack of data the more north that you go. You can see how dense the points are along the circumference and just how sparse they get towards the center.
Okay. Yes.
This is because of Messenger's slightly off polar orbit. It didn't spend as much time over the northernmost part of the planet, the part that we're interested in.
Okay.
So I mentioned how MLA provided information about the elevation and the surface reflectance. In this case, the color bar represents the reflectance.
Mm-hmm.
And we would expect water ice to have a reflectance greater than about 0.3. So in this image, it would look particularly red.
Mm-hmm.
You can see that the outer part of the circle, like the circumference, which is Mercury's regolith, is largely green, right? And it has an average reflectance of about 0.2. But as we approach the center where our craters are, towards higher latitudes, the MLA data looks increasingly red in those regions. And that's where ice happens to be thermally stable. Not a coincidence. There's probably ice there at the surface causing the MLA to be redder. So this is promising. And if we want to go to figure 8, you can see the MLA in the 4 craters more zoomed in.
Oh, okay. There we go.
So in this figure, the pink outlines the regions where ice can be stable at the surface, according to our prediction, which is back here too. So we gather from this figure a couple things. The amount of MLA data is a little bit sad. It looks quite empty.
Sparse, yes.
How many points in Trigonometer? I forget. There's like
25. I think there's really very little.
It's better than 0.
Well, there's 0 points in the cornering region, but I will talk about that. But also the MLA data does look very red, right? Most of it is confined to this pink region where we expect there to be ice at the surface. So this supports our prediction for there being ice in those regions. Right. But there isn't a lot of data in the region where low reflectance material is able to be stable. So this kind of inhibits the comparison between this high reflectance and low reflectance regions that we predict to see. So figure 9. Good.
Figure 9. And we will slide down. This is the last figure, I believe. Figure 9. Density is MLA. Okay.
So this is like the last 2 figures that you saw, but in like plot form. So this plot shows the distribution of the MLA reflectance in the regions that are outlined by that legend there. So the purple line represents all available MLA data. Since the PSRs make up a very small percentage of the surface, this curve largely represents Mercury's regolith. The yellow line represents the distribution of reflectance values in the sunlit region at high latitudes, so latitudes that are comparable to our 4 craters. This will come into play. This also represents Mercury's regolith, since we expect the sunlit region to be too warm to sustain any sort of volatiles at the surface.
Okay.
The green line represents the distribution of MLA within the PSRs of the craters. And the red and blue are subsets of that green line, representing the ice and corning regions, respectively. So yellow, blue, green, and red are all subsets of purple, and blue and red are subsets of green. What this plot is telling us, so we can see from the purple curve, it peaks just before like 0.2. So this is consistent with previous findings and is about the average reflectance of Mercury's regolith.
Okay.
The yellow curve, however, in the sunlit region peaks a little higher than that and the purple and yellow curves, they're supposed to largely represent the same thing, but they look very different.
They do.
And so we have to keep that in mind because this region has an average reflectance of about 0.34, which is brighter than the reflectance that we would expect water ice to have. But this is the sunlit region. It is surely too warm to host water ice at the surface.
Oh.
So the reason that it's so bright on average could be due to maybe an abundance of micro cold traps that have ice, or anomalous MLA points that were captured at high emission angles, which maybe could potentially result in anomalously bright values.
Mm-hmm.
And like I said, we cannot filter out all of the anomalous MLA points from our analysis because we wouldn't have anything to look at.
No favors.
So instead, yeah, this is what we have to deal with. So instead, we're comparing the sunlit region where we wouldn't expect to find ice to the PSR, to the green curve, where we do expect to see ice, which has similarly high emission angles to the sunlit region. So basically, this allows us to disregard like any effects that might be due to high emission angles because we would expect both of these regions to be affected the same by these high emission angles. They have similarly high emission angles.
Okay. Mm-hmm.
So we find that the PSR has an average reflectance of about 0.57. And the ice region similarly has a reflectance of about 0.58. This makes sense because most of the PSR can sustain water ice. So it makes sense that those are similar averages.
That does. Okay.
This is about 1.65 times brighter than the surrounding sunlit region, which is consistent with ice being present at the surface in the PSR.
Mm-hmm. Mm-hmm.
Now, the problem child, the blue curve, representing the points in the Corning region, is also very bright, but you can see that the error bars are much larger for this curve. And if you scroll up, I think, to table 2.
Table 2, let's find table 2 briefly. Table 2, there we go.
Yeah, this is the distribution of points in these regions. You'll see that more than 90% of the available points in the predicted Corning region are just confined to Kandinsky. So we can't really make any claims about that region because we have a severe lack of data and an extremely uneven distribution across the craters. I mean, there aren't any in Triglavittata at all. So we're looking at 76 Corning points to 409 in the ice region. So it's not really reliable, right? So basically from the MLA data, we figure that ice is present at the surface, but the MLA data is insufficient to really fully test our prediction of between these low and high reflectance regions.
Cool, fair enough. Very good. Go back to this figure. Very good. Okay.
Yeah, so that's basically it. In summary, we made these new high resolution DEMs, higher resolution than what has been previously published. From those, we generated models that ultimately resulted in a prediction of where to find water ice and low reflectance volatiles at the surface.
Yes.
We compared this prediction to the Arecibo radar data and the messenger data, and we found that areas of high radar backscatter are well correlated to areas predicted to sustain superficial or shallow subsurface ice. We also identified this intermediate class that could be due to variations in the ice purity or mantling of the ice or uneven abundances. The MDIS did not reveal conclusive evidence for water ice at the surface, but also the lack of evidence in the MDIS doesn't mean necessarily that the ice is not there. And the MLA analysis was consistent with previous findings that suggest water ice is at the surface of these 4 craters, but we could not distinguish between the areas predicted to have low reflectance surfaces and the areas predicted to have water ice.
Right. Very cool. Very cool. I'm going to save that part for the future here. Very nice. Beautiful work. Beautiful work.
Yeah.
And Allie and Nancy, thank you so much for walking us through your very lovely article. Cool.
Thank you.
Yeah, thank you. It's been super great to see this detailed study done for like these craters that have so much ice on Mercury.
Mm-hmm. And you mentioned, you hinted at it a little bit, and I think it was there toward the end of the article. And so let me push on it a little bit. And where do you think we go with this research over, let's say, the next couple of years? Is there new messenger data? Are there other missions coming up? Are there wavelengths? Is there perhaps more sophisticated theoretical models? So just sort of next steps, where do we go over the next couple of years on this topic?
Yeah, so we're very excited that Bepi-Colombo, the next orbital mission to Mercury, is already on its way.
Yes.
It's a joint mission between JAXA and the European Space Agency. It'll begin orbiting in 2025. So we're excited that it will collect new data for us. Bepi has a few instruments that will be valuable for this study. So it has the Bepi-Colombo laser altimeter, or BELA. This is analogous to MLA. It will take data at the same wavelength as MLA. Given Bepi-Colombo's plans for a more circular and polar orbit, we hope that it will gather more measurements of Mercury's northernmost craters, which can work to improve the models, for one, and let us revisit that reflectance analysis. It also has a camera-like messenger called Symbiosis. Nancy, you have to help me out what it stands for.
Oh, no, I don't have that off the top of my head.
Somewhere in the paper.
It was in the paper, though.
Yeah.
It's a camera, like Messenger's camera. We hope that it will capture more images of the PSRs. This is really challenging, but we're hopeful, especially for a trigonoid otter, to maybe finally determine the nature of that weird feature that we saw.
Yeah.
And Bepi also has a new instrument with no messenger analog called MERTIS, the Mercury Radiometer and Thermal Imaging Spectrometer.
Okay.
Oh, look at you. Good job.
Yeah. So we'll be able to obtain measurements of the mineralogical composition of Mercury's deposits. This can help us better understand that low reflectance material that we've modeled as cornine in the study.
Right.
So yeah, we hope that we can inform Bepi Colombo observation plans, and then we're in a position to hit the ground running once we get more Bepi data.
Awesome. Awesome. I really look forward to seeing this topic evolve over the next couple of years with the new mission coming up. It'd be really nice to see this.
We're very excited too.
Yeah, very cool.
Yeah, and I'm on the Bepi Colombo team as a interdisciplinary scientist funded by NASA. And so I know studies like this are being used to help the targeting, choose which observations to take and everything. So it's just really great to get this out there, so that Bepi Colombo can maximize the science that they're able to do.
Yeah, very nice. Cool. Allie, Nancy, thank you once again.
Thank you.
Oh, thank you so much.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.